So now that we have talked about polynomial long division and just touched really quickly on synthetic division, and we'll get a lot more practice with synthetic division in this video, I want to introduce a concept to you that could be really helpful, and it's called the remainder theorem. That remainder that we get back when we do division is more than just a remainder. It means lots of other things as well in terms of the relationship between those two functions that were in the division problem. So the remainder theorem says that the following two statements are equivalent, which means if one of them is true, then the other one has to automatically be true. So R is the remainder when dividing P of x by x minus a. So we did this division problem, and we got a remainder of R. Now there's other parts to the answer, the quotient that we get for the answer, but all we're worried about is what's going on with the remainder right now. So we've got this big polynomial, and we're simply dividing it by x minus a. Since it's linear, we could choose to do that with long division, or we could do it with synthetic division. This remainder that we get is exactly the same as what we would get if we simply plugged a into the polynomial function. So you might ask yourself, well, why would I ever work out division if it's the same as plugging it into the function? Well, some of these polynomial functions are very long and complicated. And if you don't have a calculator handy, or if you are not careful with your parentheses, there's a lot of room for error. So this polynomial could have an x to the sixth in it, and it could have negatives, and you could be plugging in a negative. And if you don't use parentheses around a negative in your calculator, you're going to get the wrong answer. So when evaluating the polynomial, there is lots of room for error as that polynomial gets larger and more complicated. So doing the function value by plugging in is not always the easiest way to do it. This says that we could also just do division, and the remainder is going to be the exact same number. And since this is a linear factor, we can just do synthetic division, because the only operations we ever have to do in synthetic division are multiply, add, multiply, add, multiply, add. We don't do any exponents when we do synthetic division. So even though the polynomial has exponents in it, we won't ever have to worry about the exponents with the synthetic division. So that's the nice thing about it. So I want to show you an example. And actually, I'll do several examples. We want to use synthetic division and the remainder theorem to find each of the following functional values. So we don't want to find these answers just by plugging the number into the polynomial. We want to do polynomial division, and specifically synthetic division, and we're going to show that we get the same answer. Now on this first one, I'm going to do it both ways just to show you that we do get the same answer. So let's say we have P of x equals negative x cubed plus 5x squared minus 8x plus 9. And we want to find P of 3. Well, all we have to do is synthetic division with 3 in the box. And remember, synthetic division, next to our special number that we use over and over and over again, we write the coefficients from a polynomial. And one thing I did not tell you in the last video, because it didn't come up, and it's not coming up here either, is that we need to make sure that if there are any missing terms in this polynomial, we put in a 0 for the coefficient. And what I mean by missing term is, here our leading term is negative x cubed. So we need to have an x squared term and a linear term and a constant term. We need to make sure there's nothing missing. Whatever the degree is, you will always have one more term than that. So this polynomial is degree 3. I should have 4 coefficients here. So first coefficient is -1, and then 5, and then -8, and 9. And notice I also pulled the minuses down as negatives. Those are very important. First number always comes straight down, nothing to do. But from there, we're going to multiply by 3. -1 times 3 is -3. And we're going to add down. 5 and -3 is 2. Multiply to go up. 2 times 3 is 6. Add to go down. -8 and 6 is -2. Multiply to go up. -2 times 3 is -6. Add to go down. 3. And remember, the last number is always the remainder. So what this says is that P of 3 should be equal to 3. We've done this kind of operation before where we just plug 3 into the polynomial. And for this one only, I'm going to show you that they're the exact same thing. So if I were to do the negative of 3 cubed plus 5 times 3 squared minus 8 times 3 plus 9. So in synthetic division, it was just multiply, add, multiply, add, multiply, add. Very simple. Here, I've got to do exponents. I've got to do multiplication. I've got to do addition and subtraction. I have to make sure I follow order of operations. You need to be very careful. There is lots of room here in this evaluating this polynomial to get things wrong. So 3 cubed is 27. So that first term is -27. 3 squared is 9, and times 5 is going to be plus 45. 8 times 3 is 24, and then plus 9. We also get much bigger numbers to work with here. Notice the numbers in our synthetic division, they're just single-digit numbers, very easy to work with. Now, I've got to subtract all these numbers together. Well, 45, I'm going to put my positives together. 45 and 9 is 54. And then I'm going to put my negatives together. 27 and 24 make 51. So I'm subtracting 51. And we get 3. Exact same answer. Less math to do. Technically, we had to do powers here, order of operations, working with much bigger numbers, where synthetic division, multiply, add, all single-digit numbers most of the time. So we get the exact same answer, either way. And that's what the remainder theorem tells us and promises us will always be true, that the remainder from the division problem will always match the functional value. So let's look at another example. Let's say we have got P of x equals 2x to the 5th minus 9x cubed plus x squared minus 1. And we want to find P of -2. I changed a couple things purposely here. Notice this is a 5th degree polynomial. That means when I write my synthetic division, there should be 6 coefficients. So I'm going to work this problem with synthetic division. That number goes in the box. And next to it, I need to write the coefficients from my polynomial, starting with the biggest. So my x to the 5th coefficient is 2. And then I need my x to the 4th coefficient. And there isn't an x to the 4th here. That means its coefficient is 0. And then I need my x cubed coefficient, which is -9 because of the subtraction. Then I need my x squared coefficient. We don't see it. We do see an x squared, but we don't see a number in front, so we can just say it's a 1. Then I need my x coefficient, just my linear x, and there isn't one here, so its coefficient is 0. And then I need my constant, and again, bring the sign with it. It's -1. So 5th power means 6 coefficients, and it's because my x to the 4th term is missing. so coefficient of 0. And my linear term, just an x without the power written, which is a power of 1, is missing, so 0 coefficient. And for synthetic division, first number comes straight down, and then we multiply times the box number, that's -4, and we add -4. Multiply by the box number, -4 times -2 is +8, and then we add. -9 and 8 is -1. Multiply by the box number, I get +2, add them, I get 3. Multiply by the box number, I get -6, add them, I get -6. Multiply by the box number, I get +12, add them, I get 11. The last number is always the remainder, and that tells me that P of -2 is equal to 11. And I did not have to plug -2 in for my x's and be really careful with my parentheses in the calculator and make sure I do 2 times parentheses -2 to the 5th minus 9 parentheses -2 cubed, and on and on and on. We get the exact same answer by working out the synthetic division and just using the remainder. So I'm going to do one more example, and this is going to help lead us into the last video for this section. We have the polynomial p of x equals x to the 4th minus 26x squared plus 25, and I want to know what p of 5 is. And we're going to do this with synthetic division. I'm not actually going to go through and plug in 5. Can you tell me right off the top of your head what 5 to the 4th is? Well, if we pull out our calculator, we can. But for the rest of your life, you're not going to be carrying a calculator around in your pocket necessarily. So we can simplify this problem to just addition multiplication of single-digit numbers, basically, with synthetic division, and understanding that the remainder theorem tells us the remainder for that division problem is exactly the same as the functional value. So 5 goes in the box. Next to it, I'm going to write my coefficients. This is a 4th degree polynomial. That tells me I need 5 coefficients. So be careful. I don't see 5 here. There's some missing. My x to the 4th has a coefficient of 1. And then work your way down. X cubed is not there, so it's missing. Its coefficient is 0. X squared has a coefficient of -26. X, just my linear x, is missing. It has a coefficient of 0. And then my constant is 25. So power of 4, 5 coefficients. And then we're going to work our synthetic division. First number comes straight down, and then we multiply. 1 times 5 is 5, and then we add. 0 plus 5 is 5. Multiply, we get 25. Add, we get -1. Multiply, we get -5. Add, we get -5. Multiply, we get -25. Add, we get 0. This means P of 5 equals 0. That's all we were asked to do, but this is really important. Having a remainder of 0 is really, really important. What this means is 5 is a 0. 5 is a number that when we plug it in, gives us an output of 0. That means 5 is a 0 of P of x. That means 5, 0 is an x-intercept for P of x. And we also said a few videos ago, this helps us with factors. That means x minus 5 is a factor of P of x. So those remainders of 0 are extremely important. They tell us a lot of stuff about that divisor we just used and that number we just used. Now, a remainder of anything else doesn't tell us anything really. It just tells us the functional value. But a remainder of 0 tells us a lot more. And that's our next theorem in the last part of this section, which is the factor theorem. And that's going to be in our last video.